Okay, now so let's talk about section 2.2, limit of a function. So intuitive definition of limit. If I let L C be constant and fx a function, then the right hand limits, or we say limit of fx from x go to c plus over here, right, equal to L. Let's say the value equal to L. Um, if the value of fx approach L as x approach c through values greater than c. Okay. Okay. So let's see if so I also have example 2 here. It's a finding the limit graphically and fill in the limits of for the graph gx below. So we're gonna look for the right hand limits. So which is the one that have a plus sign, right? This one is plus sign. This one a plus sign. Okay, but this one not, right? So let's take a look at the right side. It say that if the value of fx approach L as x approach C. Okay, so x approach C. C in this case is 2, right? C equal to 2, right? Uh, x approach C through values greater than C. So what does that mean? I have 2x, x equal to 2 was here, right? And and it say x approach C through the value greater than C, which means you go like this, right? Go to C for the x value, and it say like the limits of fx equal to L if the value of fx approach L. Okay, so uh, according to the value of x go to here, you know that's the value of y. Let me use the other color. The value of y just go like this way, and it's approach to this point, which is 1, right? Which is 1. You see that? So I can write this to be equal to 1. Okay. What about 5, right? From a right hand limit of 0x to 5, right? So I know that, let me change this. I know that's now it here, use the other color. Now we come here at 5, and it's 1 go from the right hand limits, right? So it's go by the 1, the value that's greater than 5, greater than 5. So it's go this way, approach to 5, right? So okay, so this gonna be, tell me here. Okay. Now for the LX, it's trying to go to, let me use either color right here. The graph trying to go to approach to the value approach to here, this point, right? When x goes to 5, so then I know that it is will go to here, this value. All right. Even though I know that as x equal to 5, right? F of x will be equal to this, f of x will be at here, where it's 1. But we are talking about the limit, right hand limit. We're not talking about the value of y. So we try to imagine where is g of x right now, trying to approach to. I know that it's trying to approach to this point. And at that point, the value of g of x is going to be equal to 2. So then I put 2, okay? So don't put 1 in here because this value of 1 over here, that just is a value of g of 5 equal to 1, okay? Which is not the limit of gx when x go to 5 from the right hand side, okay? So remember that. All right, so now we're going to talk about the left hand limits. We say limits fx equal limit of fx when x goes to the c minus, which is c from the left hand side, equal to L. If the value of fx approach L as x approach to c through the value smaller than c. Okay, so in this case, let's take a look at A, because I have c is 2 minus over here, right? And what else over here? 5 minus, right? Okay, so A and D. So we're gonna try to figure out for the A first. At 2, so take a look at 2. So here at 2. Okay, we're gonna try to see the x approach 2 to the value smaller than 2. Okay, which is the left hand side go to this, right? And come back with the graph. I know that graph, it just go along like this and try to approach to here. So the value of y at that point was 3. So I'm gonna put 3 over here. Okay. What else? For the phi negative over here, limits of g of x when x go to the phi from the phi negative, which means from the left hand side. Okay, so let me change the other color. Maybe the yellow, the orange one. Okay, so where's phi? Let me delete this one. 5 over here, right? From the left hand side. So here, right? Try to move to here. Oh, okay. So now I have to delete this one so you can see, right? So go along with the graph is go by this way, right? And from the left hand side is go to that point. So you will have the value of g at this one will be equal to 2. So I will have 2 also over here. Okay. Now let's talk about the limit. We say limit of fx equal to L if limit fx for x go to c from the right hand side equal to L and equal to the limit of fx for the x go to the c from the left hand side. So in this case, what does that mean? You need to have the both sides limits should both hand limits should be equal each other, right? And in order to get the limit of c, right? So let's take a look at the limit of c of g of x when x go to 2. You will need to take a look at both side when x go to the 2 from the left and x go to 2 from the right is not equal each other, right? So you see that limit of g of x for x go to 2 from the left hand side not equal to limit of g of x when x go to 2 from the right hand side. You see that? So in this case, it's not satisfied for this definition, right? So what I should say in here, it just gonna be undefined. Okay, undefined, or just I'm gonna notate like infinity over here. You can say undefined. Actually, I'm gonna just say undefined. So you don't wanna undefined. Okay, and what about for g of x when x go to 5 over here? You will see the left hand side equal to 2, the right hand side also equal to 2. So they equal each other, then it's satisfied for the definition of limit over here, and is in this case we can just write as equal to 2. Okay, so far so good. All right, now let's move down. We're gonna try to work on this one. Okay, fill in the limits of the graph of x below. Okay, for x equal to 2 again for the left hand side. Okay, so x go to 2 again for the left hand side, right? What happened with the fx? I know that fx will go along with this and go to try to go to this point. And what is value of this point? This is 3. Okay, so I put 3. Okay, now I'm gonna clean this up. I'm gonna try the limits. X when x go to 2 from the right hand side. Okay, right hand side. Let's go like this, right? Okay, so the fx will be go like this along to the graph and try to reach to this point. Okay, and what is the value of this for y value of this point? It is 1. So you see that if you compare for the fx when x go to 2 from the left hand side and when x go to the 2 from the right hand side, then they are not equal each other, right? Not equal each other. So then what is your conclusion for the limit of fx when x go to? Do not exist, right? Or undefined. You can write do not exist in this case, or undefined. Yep. What about, okay, what about f of 2? Okay, what is this value of fx when x equal to 2? So if you take a look at x equal to 2 over here, right? What is a point that has the value of x equal to 2? Is that this one or this one? Remember that the whole or the open circle over here it means that there is no point in here. There's a hole of the graph in here. So you cannot have a value of Fx at this point. It can happen only for the limit, but if you're asking for the value of Fx when at this one, then there's no value there, right? Now, for the closed circle here or closed point over here, it actually means that there is a point that stay in here. We have the value of x at 2. Then you can find the value of y for this point gonna be equal to 3. And you put f of 2 gonna be equal to 3. Yep. That's to be it. Okay. Now we're gonna move to the limit of fx when x equals to 4 minus, which is from the right, no, sorry, from the left hand side to 4. Okay, let me clean this up. Okay, now it's from 2 to 4. Okay, 2 to 4. You know what? Let me just keep on and on. All right. 2 to 4. Let me go too close to 4 from the left hand side. This is matter where to where. Then what happened with the graph? It just go along with the graph over here. Go along with the graph and try to reach to this point. What is the value of y at this point? It is 4. 4. Right. Okay, so move to the right hand side, limit of the right hand side to 4. Okay, so delete this. First, for x greater than 4, go to 4, close approach to 4. Then you have from here, you go to here. Right, you see that? Then you have 4, also 4. So you see that for the limit of fx when x go to 4 from left hand side and right hand side, they are equal each other. So then it's satisfied for the definition of the limit, and you can write the limit of x when x go to 4 equal to 4. Okay. Last question. F of 4. Now be careful. In this case, you are looking for the value of fx when x equal to 4. Okay, I know that when x equal to 4 is here is a x equal to 4. Now you try to look, is there a point that's on the graph have value of x equal to 4? But look, the graph has a hole. In this case, it doesn't have any point that's satisfied for value of x equal to 4. Okay, so in this case, I'm gonna say undefined or do not exist. Okay. Now let's have there's most activities in this activity is conserve continuity. Okay, so let's skip this one and we're gonna talk about that in the class if needed. We're gonna move to the example number 3. creating a table. We given fx equal to cosine x minus 1 over x, and we're gonna find limit of x when x goes to 0 if it exists. You actually can use Excel on a laptop or the calculator or the phone in order to solve this one. So let me show you. For this one, if you use Excel, it could be very easy. So Excel, again, yep. I have X and I have cosine X, X minus 1, and then maybe I need to have divided by X. So yeah, that's right. Copy this one. Okay. So if X equal to 1, then what happened with the Lx? I'm gonna click on equal to, and then paste it down. I will have this X. I'm gonna change to be equal to 1, and this here also equal to. Click on this one because you know that we are changing the value of X. It's A2. I click on that, right? Okay, so now is gonna be equal to 0.4597 something. I'm gonna put 0.1, 0.01, 0.001, and 0.0001. Okay. And for the last step, I'm just gonna click on the first answer and then move to the right corner of that, and then hold it and shade it until the last row. So you're gonna see the answer when you click on that. So you will see it's becoming closer and closer to 0. See that? So the answer here, let me write it to the notes, gonna be negative 0.45968, and the next one is 0.049958. The next one will be negative 0.004999, and then next one will be negative 0.000499, and the last one will be negative 5 times 10 to the power negative 5. So actually I can divide it as 0.0000499. If you use a calculator, like TI-3 or 4, it should be similar like that. And you can say that note 0 is not in the domain, because if you have x equals 0, right, then this this rational equation will be undefined. Okay, so Lx. So, and you can see from the table here, it look like limits go to 0, close to 0, right? Okay. When x go to 0, s like go to equal to 0. All right. And if you use decimals to watch to draw this one, uh, actually, you know what? I can go ahead and draw. First one is 1 here, right? And it's go down to is go down when x equal to 1, I have negative 0 negative 0 let me see. So I say here is negative 0.45. So it's about for 6 about here, and it's keep going smaller and smaller to 0, right? Okay, so that's just from the information in the table here. But let's see in the decimals, what is that look like? So you have y equal to cosine of x minus 1 divided by x. So it look like this. Let me make this bigger a little bit. So 1 was about here, right? All right. So if you want to see clear, okay. So it's look like this. Let me see. So it touch y over here, 6. So yep, look like we have that. The graph look like that. So yeah, so maybe go a little like that. Or more too quick. Something further, all right? And like that. Okay. Kayak. All right. Just try to show you how to make it on decimals. Now let's take a look at example number 4. We're going to talk about infinite limit. Let's do example number 4. Find the limit of 1 over x squared when x go to 0 and if it exists. So if you create a table for the for this function, if x equal to 1 over x squared, you have you take a look at the x go to 0 at, from the right hand side, right? This is the right hand side because it's the x value is greater than 0, right? And for this is x go to 0 this way from the left hand side. You can see that the value of fx 1 over x squared become bigger and bigger, right? And I'm gonna say it's become like infinity later, like as a graph over here, it keep going up, right, until the infinity, positive infinity. Okay, so what's the definition? I left f be a function defined on both sides of A except possibly at A itself, then limit of x when x go to A will be equal to infinity. Okay. It means that the value of x can be made arbitrarily, arbitrarily large as we please, and by taking x sufficiently close to A but not equal to A. Reminder, the limit does not exist. We notate by DNE, but using infinity is more descriptive and gives more information than just say D and E, right? Similarly, we can also have limit of fx when x go to a equal to the negative infinity if fx can be made arbitrarily large negative, right? So take a look at one side limits in example 5 of here. If we are looking for the x when I go to 0 from the left hand side, right, the left hand side over here, it's actually, you see that it's keep going up and up to the positive infinity, right? So you will have a positive infinity. For the limit of fx when x go to 0 positive, which means the right hand side, right? 0 was here, so it's go like this, right? It keep going down to negative infinity. Okay. At 2, you see that from the for the x when x go to 2 from the left hand side, and let me use another color. It's just going up, right? You just see that until the positive infinity. Similarly, from the right hand side to the 2 over here is will also go to the positive infinity. Now for the limits of x when x go to 0, you can just say do not exist. And also uh, um, for the limits of x when x go to 2 is just gonna be positive infinity. Okay. Because the first case for the x go to 0, one hand side is going up, right? The left hand side going up, the right hand side going down. So you can have D don't exist. For the limits of fx when x go to 2, it both go to the positive infinity. So instead of saying we should actually say positive infinity. So you can more have like more descriptive than information than DNE in this case. Okay. Now another definition about vertical asymptote. The vertical line x equal to a is called a vertical asymptote of a curve y equal to fx is at least one of the following statement is true. So limit of fx equal to positive or negative infinity. That's for x equal to a. That's going to give you a vertical asymptote. Another case have another one is limit fx equal to positive for x go to a um, from the left hand side gonna be equal to positive negative. If you t, then it's also then it is a vertical asymptote, and for the right hand side it's also gonna be equal to positive t. So that's gonna give you a vertical asymptote. All right, so a tip for pros. Vertical asymptote show up where the denominator equal to 0, right? You see denominator, you want to find the vertical asymptote, you can just make the denominator equal to 0. Okay. So let's see an easy case. For example, example 6. 1 over x minus 3 square. I remember that's there is no cancellation with the numerator. Okay. So what does that mean? It means that there is no common factor between top and bottom, so you can cancel it. You cannot cancel it, right? So example 6, fx equal to 1 over x minus 3 everything square. If there are vertical asymptote, if you make the bottom x minus 3 equals 0, remember that's top bottom here doesn't have any common factor, so you're fine with that, and there's no cancellation. So you're just gonna have x equals 3 is vertical asymptote. VA here is vertical asymptote, okay? Let me notate here. VA, okay? And okay, let me circle this. You have the answer. I really like if you guys circle the answer, so reader can easily understand. So for the example number 7 is harder case. You have x squared plus 2 on the top. Bottom is x times 7 minus 2x. So what you do is again check if there is any common factor between top and bottom. In this case, no. Then you can just make the bottom. Make the bottom is x times 7 minus 2x equals 0, right? Then what you do is using 0 factor property, you have x equals 0 or 7 minus 2x equals 0. So you have x equals 0 or x equal to 7 divided by 2. Okay. That's going to be the vertical asymptotes. They are vertical asymptotes. Oops. All right. So in order to draw in this case, you should know that the graph was at 0 here, and then another one is 702 here. There should be a vertical asymptote here, right? So vertical asymptote, the first one is actually the y axis. Second one is x equal to 7/2, right? So the graph have to will not go through these two vertical asymptotes, but go along with it. So if you try to work on decimals, you will see that the graph will look like going along to the x equals 0 and go down for the one in the other hand side from the right hand side to 0 is just going up to infinity. Actually, what I gotta and for the left hand side go to 702 is go up also, and the lastly is go down when x go from the right side to 702 and go along later on is go along with the y-axis. Okay, you can check it on the decimals to see the graph and understand. So number 8, let's talk about the wholes. Okay, so as I stated before, make sure there's no common factor between top and bottom. So for this case, if you try to factor it first, okay, so let's try to factor, and we have fx will be equal to x minus 1 times x plus 1, because it is the different two square, right? So you can apply the formulas for this case is we can be a factor as x minus 1 times x plus 1, and bottom stay the same at x minus 1. So in this case, what happened? You have common factor between top and bottom, and you can cancel x minus 1 factor if x not equal to 1. Okay, because so I gotta say that x not x equal to 1 is not in the domain, right? And then so in this case now we just have fx going to be equal to x plus 1, which the domain is x not equal to 1. However, in the original form, we can have x equal to 1, right? As we can have x equal to 1. So there is a hole at x equal to 1. So whenever you see a common factor between top and bottom, then that factor, make that factor equal to 1, equal to 0, then solve it is going to be the value of x of the whole. Okay, so yep, how the graph apply is actually look like a line, look exactly a line. Okay, like this. However, this line will have a hole at x equal to 1. So here is 1 hole here. Okay, so That's it. Let me move to exercise to try number 3 here. I will let you guys to try on this. And then we gonna talk on it in the class later. Also, you guys can try exercise number 4, and we're gonna work on that later in the class. Okay, and we're done with section 2.3, and I see you in the class later. Have a good day.